window. Click Windows, second option.
Okay.
Directly you will go to what are the windows opening in your system, and you have to select your PPT share. That's also. Select the PPT, then you click it to share.
Yeah, 1 minute, sir.
Yes, sir. Yes, sir.
So present window, then where I should go?
Then you will get what are the opening windows available in your system. In that you have to click PPT, sir. In that click PPT presentation. Then you give share, sir, share option.
Okay, let me just check, but it is not showing. 1 minute.
Okay, sir, please, sir. Yes, sir. It is presentation started. I think. Have you selected the PPT, sir?
No, it did not come. It did not come there. I'll stop it.
Okay. Or you will try with your entire screen, sir. Is it possible, sir?
Let me check. Only one screen comes there, but this thing is not coming. Desktop thing is not coming there.
Okay, sir.
Just 1 minute. Give me 1 minute time.
Yes, sir. Please, sir. Please.
Okay. That option is not coming, sir. It says only share an application window.
Okay, sir.
Chrome wants to share the content of your screen with the Meet Google. Choose what you'd like to this thing.
Is there any option, sir? Yeah, window. Is there, sir?
No, nothing is there.
Okay.
1 minute.
Okay, sir.
No, nothing is there. I think you have not given me access or something.
No, sir. It is given the same link only, sir. Otherwise, we will do one thing, sir. Just you leave this meeting, then you join once again, sir. We will check once again, sir.
Okay.
Yes, we will try it, sir.
Yeah.
Yes. சார் சொல்லுங்க. மியூட். 1 minute, sir. Sir, good afternoon, sir. Sir, first you can open your PPT, sir, in the presentation mode. Requesting, sir. Sir, your mic is in mute mode, sir.
Yeah, it is open, sir. Presentation is open.
Okay. Now you go to share now, sir. Present now. In the screen, present now option is there, no? Now you go to present now, sir.
Okay.
Yes, sir.
Yeah.
Now you will get the 3 options, no? Your entire screen, a window, a Chrome tab. In that, a window, sir. You click a window.
Now I'm getting only one option. That's the problem.
What is that option name, sir?
1 minute. Yeah, it is there now.
Yes, sir. Yes, sir.
Yeah.
Yes, sir.
Is it coming there? Not yet, right?
Yes, sir. Yes, sir. Please go to slideshow mode, sir. It will be visible to all, sir.
Is it?
Yes, slideshow mode. It is visible to all, sir. Yes, sir. Yes, sir.
So can you see my first slide, the title slide?
Yes, sir. Yes, sir. We are seeing, sir. Yes, sir.
Okay, so it starts at 2 o'clock, right? So,
I think just 1 minute, sir. I will ask our admin team. Shall we start?
sure, sure.
Please, please.
Yeah.
Good afternoon to one and all present here. I welcome all the participants to this 5-day short-term training program. Now we are going to start this third day, second session. Once again, thank you for joining with us. Now let me introduce our resource person, Dr. Harish Barshilia, sir, Chief Scientist, Head Surface Engineering Division, National Aerospace Laboratories, Bangalore. Dr. Harish C. Barshilia obtained his M.Tech and PhD degrees in physics from the Institute of Technology, Delhi in 1993 to 1996. He was a postdoctoral fellow at the University of Missouri, St. Louis, City of University of New York, USA, during 1997 to 99. He had joined the CSIR National Aerospace Laboratories, Bangalore in 1999. He had published 197 peer-reviewed papers in the internationally reputed journals, 31 papers in conference proceedings, 4 book chapters. He is the inventor of 20 patents, including 10 international patents. He has contributed 95 papers in national and international conferences. He has delivered 110 invited lectures, including plenary and keynote in India and abroad. We are honored, sir, for joining with us. Now I request our resource person to proceed with the session. Before I request all the participants, please mute your video and audio. Please, I request all the participants, please mute your video and audio and don't present your screen in between. I am requesting once again, sir, all the participants, please cooperate for the smooth conduction of the program. Sir, now I request our resource person, sir, please, sir, you can proceed, sir.
Very good afternoon to all of you. Thank you, Professor Reddy, for a nice introduction. May I know how many participants are there?
Yes, sir. Now here in the YouTube, it is around 70 plus, sir. And in the YouTube, it is more than that, sir. Here, present Google Meet, we are having 70 plus.
Okay.
Yes.
So what is the background? These are faculty members or students also?
No, only faculty members, sir. Only faculty members.
From mechanical engineering or what?
Yes, sir. Mechanical engineering, faculty members and research scholars, sir.
Okay. Okay, so very good afternoon to all of you once more. I'm going to give you some insight on our research in the area of nanotechnology inspired materials and coatings. As you are aware that I come from National Aerospace Laboratories, so I'll try to cover the applications of these nano coatings in the area of aerospace. There are large number of applications of these nanomaterials and nanocoatings, but we'll confine ourselves to aerospace applications only. So we work in the area of surface modification technologies. Just to give you a glimpse of what are our activities here at Surface Engineering Division of CSIR National Aerospace Laboratories. National Aerospace Laboratories, as such, we work mainly for the aircraft program. We have two civilian aircraft programs, such as we call them 14-seater SARS and the next generation SARS, that is 19-seater. And we are also working on regional transport aircraft, which is about 90 seaters. And we have another aircraft program wherein we have 2-seater and 5-seater aircrafts, which are being supplied to the sports clubs and the other hobby clubs. So there are about 20 technical divisions. It's a huge lab of CSR under Ministry of Science and Technology. So under this, at NAL, we have about 20 technical divisions, like 20 departments. So I'm heading the coating technology department. So we work in the area of large number of coatings, such as solar absorber coatings, which of course I'm not going to touch upon today, solid oxide fuel cells, thermal barrier coatings. We have a major program on sensors wherein we develop like giant magnetoresistant sensor, pressure sensitive paint, oxygen sensors for automobile industry. We also have a major program on stealth coatings. They are very highly strategic materials, mainly for 5th generation aircraft, the kind of thing you hear in like the Rafale and other F-35 kind of aircrafts. We also work on transparent conducting oxides, so some of the work I'll be presenting over here. And our core strength is in the area of corrosion and tribology, wherein we use different methods, both physical vapor deposition processes and electrochemical processes and other surface modification processes such as plasma nitriding. We do some work on biomedical applications such as surface modification of titanium alloys for various prosthetic applications, nickel titanium alloys for making the artificial heart valves. Then we also work on various engineering aspects of various nanopowders and micropowders. We have the capabilities to develop various oxide powder, nitride powders, and carbide powders, and then they can be used for various engineering applications. Our recent research in the area of nanoscale has been to develop various nano-inspired coatings, such as based upon carbon nanotubes, graphene and its derivatives. Of course, we also work on in the area of molybdenum disulfide and those kind of materials. And we have very good facilities in terms of both the deposition and characterization. You can visit our website, nal.res.in/SCD. So, Professor Reddy, these participants are, they can ask the questions, or what is the, how this goes?
Sir, good afternoon, sir. After end of the session, they are going to ask you questions, sir.
Okay, so I'll continue, okay?
We'll continue up to the end of the session, and we'll give time to ask the participants to ask the questions.
Yeah, in between, if they have some sort of clarification. for some time.
Okay, sir. Okay, sir. Thank you very much, sir.
So I want to make it more interactive rather than monotonous.
Okay, sir. Okay, sir. Welcome, sir.
Sorry to disturb you, sir.
Yeah.
Sir, we are seeing your next slide and other things also. Your important slide is in the smaller manners, the smaller size.
So
Can
you
you
go
make
to slideshow, sir. Slideshow.
Yes,
One minute, one
yes.
minute. This technology is too difficult. 1 minute.
Okay.
In this, it is now 1 minute.
Go to slideshow, sir.
1 minute, sir. Um, in my PPT, I should go to slideshow.
Yes, sir. Yes, sir.
Yes, sir. Yes, sir. Click first slide, sir.
Yeah, 1 minute, sir. One minute, sir. 1 minute.
Yes, sir. Yes, sir. Please, sir.
Take your own time. So keep 100% and again at the left side, you have a slideshow.
In your Google or where?
Where in the PowerPoint only, sir. PowerPoint only.
PowerPoint I am doing, but it is not going. Some problem. Just 1 minute, sir.
Sir, no problem, sir. Now it is okay, it seems, sir.
No problem. I'll correct
yes,
it. I will correct it. Don't worry.
Okay.
Now how it is, sir?
Again, we are seeing next slide, sir. Previously, it is good, sir. Just now, just a few seconds back.
Okay. Just 1 minute.
Yes, sir. This is okay, sir.
Is it okay?
Now it is changed again, sir.
It is something is happening. 1 minute.
Okay. Now it is okay, sir.
You can see the slide.
Yes, sir. Yes, sir.
Okay, I'll manage with this one only.
Slightly bigger, sir. Slightly, sir. Yes, sir. You can. Yes, sir. Yes, sir. Okay, sir. Okay, sir. Now the letters also visible, sir. Okay.
Now the problem is that I am not able to see full slide here. 1 minute, sir. It is some problem. Just 1 minute.
Okay, sir.
If I go to view slides, it is going here like this.
Okay, sir. Okay.
Sir, right side you close. Sir, you do one thing, sir. Right side close the next slide top.
Should I close that?
Yeah, yes, sir. Top.
Yeah.
That one. Yes. Close that one.
Okay.
Yeah, is it visible to you, sir, now?
Yeah, I can see now, but again it has gone back to that old only.
Yes, sir.
It has gone back to old only.
Yes, sir.
Okay, just I'll call my IT guy. Just 1 minute. Please just give me. Excuse me for
Okay, sir. Okay, sir.
I request all the participants please wait for 5 minutes because some technical problem we are rectifying. Our resource person is getting to join. I request all the participants please wait for 5 minutes. Our resource person is ready to join. Please wait for 5 minutes.
Sir, please ask the participant to zoom the slides. It's clearly visible.
Okay, sir. I request all the participants please zoom your view. Then it is visible. Your entire slide will be visible. I request all the participants please zoom it.
Just 1 minute, sir. 1 minute.
Okay, sir. Okay, sir. Take your own.
Is it better or it is same?
Actually, now it is okay, sir. But whenever you are sharing, it is changing. I think.
This one is okay. Is it visible or
slightly bigger, sir?
You want slightly bigger?
Yes, sir. Yes, sir.
The moment this one.
Yes, sir. Yes, sir. Immediately. Yes, sir. Immediately this changes. Sir, no problem, sir. You can proceed. I ask the participants to zoom the screen so that they can able to see, sir.
No. Let me try. Why this is happening? Actually, we use some MS Team and all those things. 1 minute.
Okay, sir.
1 minute.
Sir, press hide presenter view.
Huh?
Press hide presenter view.
Is it now?
Now it is okay, sir.
Now it is okay, sir.
Okay, sir.
Hola.
Yes, sir.
Yes, sir.
Thank you.
Yes, sir. Excellent, sir.
Okay, sir. Thank you.
Okay. So I'll start once more, I think.
Yes, sir.
Good afternoon to all of you. I'm sorry for those technical glitches. I welcome all the participants, and I also thank Professor Reddy for giving a very nice introduction about me. Today I'm going to present you some of our work in the area of nanotechnology, both the materials as well as coatings, which are mainly used for the aerospace applications. As you know that nanotechnology is a very vast area. So I have focused my presentation only to aerospace applications, some fundamental kind of aspect I'll be covering. I believe the participants, they have some sort of knowledge, basic knowledge of the physics, material science, and mechanical engineering. Is that correct, Professor Reddy?
Yes, sir. Yes, sir. Correct, sir. Correct, sir.
Yeah. So there is no chemistry, and then wherever you have any problems in understanding, please you can either send some sort of message to me, and or you can directly ask me the questions. So I think I could not convey you that at National Aerospace Laboratories we have various aircraft program. We have our own 19-seater and 14-seater SARS aircraft program. We have 2-seater and 5-seater aircraft program. That is, we call it Hansa, which is being used for mainly for the sports clubs. We also contribute to the research for light combat aircraft, that is a Tejas aircraft, which is being produced by ADA as well as HAL. So apart from these things, we do a lot of research for the industry as well as for the aerospace companies. There are about 20 technical divisions, and one of the division is Surface Engineering Division, wherein we develop a variety of coatings for both the engineering sector as well as for the aerospace sector. And I'm heading this Surface Engineering Division. So we do a lot of work in the area of surface modification technologies. In the area of energy, we develop a large number of solar observer coatings. Of course, today I'm not going to cover that one. If somebody is interested, they can write to me or they can talk to me. I will. We also work on thermal barrier coatings, which is a very important area in the turbine development, turbine engine development. And we also have a major program on solid oxide fuel cell. Now, in the area of sensors, we develop various state-of-the-art magnetic sensors, such as giant magnetoresistance sensor, pressure-sensitive paint sensor, oxygen sensor, mainly for the automobile industry, as well as for the pilot life support system. Being in the aerospace sector, we work on strategic materials such as radar absorbing coatings and invisible materials and coatings. We also work on transparent conducting oxides, which are transparent, but they are electromagnetically they have some unique properties. Our core strength in the department is in the area of tribology and corrosion. So I'll show some of the results wherein how the coatings and the surface modification can be used to increase the performance of various cutting tools. That kind of thing I'll be addressing. We have a large number of processes, both the dry processes, we call them physical deposition, and the electro deposition. We do some work in the area of biomedical devices, wherein we give surface modification technologies for titanium alloys, which are used for prosthetic devices, and nickel titanium shape memory alloy, which is used in the development of various heart valves or stent. I'm sorry. We have a major activity in the area of ceramics, wherein we develop a variety of nano size and micron size powders, and then we use these powders to develop various technologies such as tape casting technology. I'll briefly discuss those kind of aspects in my presentation. And recently we have started working on various CNT and graphene based materials, and also MOS2 and other kind of newer generation materials for various strategic applications. We have a track record of delivering the technologies to the industry. So on the left-hand side of the slide, you can see that these are some of the technologies. But over the years, we have developed about 50 to 60 technologies which have been transferred to the industry. And we have state-of-the-art deposition as well as characterization facilities. You name all the facilities, any facilities in the area of coating development, we do have all these kind of facilities. So I recommend you to go to our website, that is nal.res.in /SED. Shall I go to the next slide, sir?
Yes, sir. Yes, please.
The outline of my talk is like this. I will just give an introduction and then various kind of coatings like protective coatings, optical coatings, nanocomposite coatings, some of the oxide coatings, they are transparent. Then fabrication of nano powders, then template assisted growth of nano devices, and some plasma assisted based processes to develop newer kind of materials. So this is my outline, and briefly, I'll also touch upon, as I mentioned, that this graphene and its derivative, how they can be used for various engineering as well as aerospace applications. So, as I mentioned in the first slide, that we use both the physical vapor deposition as well as wet processes to develop these kind of coatings. So, to give you an example, that the physical vapor deposition process looks like this. We have a chamber which is evacuated by using suitable pumps, and then a gas, basically an inert gas of say argon, is kept at a particular pressure in the chamber, and then we apply some sort of potential to this these two electrodes in the vacuum chamber, and then you find that the fourth state of matter, that is plasma, is generated, which is nothing but a collection of electrons, positive ions, negative ions. For example, now this plasma can be achieved by way of simply applying the potential between two electrodes, the way we do in our tube lights, in our home tube lights. Or you can give you can apply very high temperatures, and then the sublimation of material takes place. So, for example, if you take a titanium plate, which is widely used in your mechanical engineering application, and if I put a titanium plate in this plasma, and then if I bias this titanium plate to a negative potential, so these positive ions, which are argon ions, they'll be attracted towards this titanium plate, and in that process you'll find that there will be some sort of momentum transfer, and if the momentum transfer is sufficient, you'll find that there will be some sort of dislodging of the titanium atoms from the plate, and then those atoms you can collect on a given substrate. You can have metal coating, for example, starting from few monolayer, few nanometer to few angstrom. And the beauty is that if you add some other reactive materials such as nitrogen or oxygen, you can very well form various kind of other materials such as titanium nitride. You can form titanium oxide. You can form titanium oxynitride. A variety of materials, or titanium carbide if you apply some sort of if you insert some methane or acetylene in the vacuum chamber. So this is how the physical vapor deposition works. So we have a large number of facilities to develop these kind of materials, both on the laboratory scale and the industrial scale. So this is a typical system wherein we can deposit like metal, we can deposit semiconductor, we can deposit ceramics, we can deposit insulator, we can deposit a combination of these materials also. So we have the ability to develop a large number of coatings with the desired composition and microstructure. So we can have the sputtering can be like a normal sputtering. You can have like DC sputtering. You can have RFIDC sputtering. You can have co-sputtering. That means two materials we can deposit together and you can form a composite material. So, for example, you want to form titanium carbonitride, which is widely used in the cutting tool industry. So what you can do is that you have two titanium targets, and then you can insert the nitrogen and oxygen in the chamber, and then you can either deposit titanium nitride, or you can deposit titanium carbonitride, or if you allow some sort of oxygen in the chamber, you find that you can deposit oxide also, titanium oxide. So this is we have a gamut of possibilities wherein you can develop a large number of coatings. So this is another sputtering system wherein you can see the cutting tools like drill bits are they are shown in the bottom right bottom photograph, and then there is a planetary rotation which will allow that you get a very uniform coating even on the complex shape kind of materials. So this is another system. We call it ultra vacuum magnetron sputtering system. See, vacuum is required for all these PVT processes. So depending upon the level of vacuum, I'm sure you must be using some rotary pump wherein the vacuum you can achieve is -3 millibar. But when you are talking about like these all your chips which are used in the your computer, like the Intel computer, wherein the 7 nanometer technology where they use, so there the vacuum levels are very very high, and we call that ultra vacuum magnetron sputtering system, and other gas molecules to get incorporated into the your device. So whenever you are fabricating these high-end sensors, for example, Intel devices or any magnetic sensors, then we make sure that the vacuum levels are very, very high. So these are another you can see the vacuum levels. You can see -8 to -10 millibar kind of vacuum levels can be achieved in these systems. And please mind it that most of these systems have been designed and developed in the country itself. So we have the expertise to design and develop these kind of they are highly sophisticated systems, and then we use highly sophisticated pumping station to create the vacuum to the tune of -9 to -10 millibar, which is very very high vacuum. Now these are some of the nanostructures. I'm sure the slides are legible and I'm audible there.
Yes, sir. Yes, sir. Visible and audible.
Okay, so these are some of the nanostructures, because the focus is on the nano materials. We can just see that nanorods of zinc oxide, nanowires of zinc oxide, carbon nanotubes, the nanoneedles, again nanorods, then super hydrophobic surfaces. So these are some of the structures which you work on the laboratory. Then nanorods of metals, then template assisted growth of like various membranes, wherein the diameter of the pore is about few nanometer, nanocapillaries, and then nanofibers, nanoparticles, graphene, and so on and so forth. There are a large number of these all micrometers. Whatever we are seeing is done by our students, and these are some of the selected ones. We have done maybe more than 200 to 300 new materials. Their microstructure has been studied and their properties have been studied. So now this is the development of hard coating, mainly for machining of aerospace applications, alloys. As you know that machining of, for example, superalloys, if you take inconel and nimonic, and if you take conventional cutting tools such as HSS or M2 or M40 or tungsten carbide, they have certain limitations. Of course, tungsten carbide can work up to some extent, but if you take HSS and if you want to machine superalloys of, say, inconel and nimonic, it is next to impossible, because the cutting edges and the other kind of features of the tool will get blunt in no time. And so if you want to have a cost-effective solution, so what you can do is that you can apply a very thin coating of, say, titanium nitride, which is a very well-known material, and it has a golden color. But titanium nitride has certain limitation. It can operate only up to, say, 400 degrees Celsius. It cannot go beyond 400 to 450 degrees Celsius. But when we are machining these materials, you'll find that the temperature goes to about 800 to 1000 degrees Celsius. So we've done a lot of work on, we call them nano-layered, multi-layer superhard coating. Superhard means the hardness of these coatings is greater than 40 gigapascal. 1 gigapascal is 100 kg per mm square. So we know diamond is the hardest known material, which has a hardness of about 100 gigapascal. So in these materials, we can achieve the hardness to the tune of about 50 gigapascal. titanium nitride, if you see, hardness will be about 20 to 25. So in these kind of nano-layer, multi-layer coatings, you can see on the right-hand side one cross-sectional TEM image, wherein you can see the distinct layers of titanium nitride, niacinamide, a typical multi-layer coating. So because of the various interfaces present in this coating, and also because of very small layer thicknesses, you find that the propagation of the dislocation becomes very, very difficult. And as a result of that, you find that the material exhibits very, very high hardness and high toughness. You might be knowing that even though diamond is the hardest known material, its fracture toughness is very, very low. If you hammer it, it will break in pieces. But these kind of materials, you find that the toughness is also very, very high. So we have worked on various nitrides, oxides, and carbides kind of material, and we have done extensive studies to see how the performance of these cutting tools can be improved by using these nano-layer, multi-layer coating. So if you are interested, you can refer this book, wherein our work is published in detail. So I'll encourage you to go through this book. This is from CRC handbook from United States of America. Now, just now I spoke about the nano-layered multi-layer coatings. So that means to say that we have two materials. They are deposited in the form of layers, and then the interfaces should be very, very flat. But now this is good for the laboratory conditions. But if you want to do actual experiments for the industrial applications, then it becomes a little difficult to achieve those kind of multi-layers in the actual production line. So ideally, an engineer would like to have a coating which is a single phase or single phase but multi-component. So for example, I can have a nanocomposite of say titanium nitride, silicon nitride, and then by controlling one of the phase, it is possible to control the physical properties of these coatings. So on the right hand side, you can see the hardness versus the amorphous content, amorphous carbon content is in particular titanium nitride amorphous carbon nanocomposite coating. You can just see that at a carbon content of about say 15 to 16%, you find that the hardness is as high as about 50 gigapascal, which is very high, and which is close to that of the artificial diamond. And the most important thing is that the grain size on these coatings is of the order of say 5 to 10 nanometer. So the grain boundary sliding comes in the picture, and then you find that the not only the hardness, you also improve the toughness of these materials, and you can just see that these kind of concept can be used for coating various cutting tool materials such as drill bits and inserts and things like that. Another important aspect in the mechanical engineering is the super toughness. That means as I mentioned some time back, even though diamond is the hardest known material, but you find that its toughness is very, very low. If you hammer it, it has two limitations. One is that, or three limitations. One is that its toughness is very, very low. So whenever there is an impact is there, the diamond will get fractured. The second limitation is that the temperature. So if you heat diamond to more than say 400 degrees Celsius, then you'll find that diamond converts to carbon dioxide, and then you find the coating or it gets vanished. The third limitation of diamond is that it cannot be applied on the ferrous material. There is some sort of inhibition between the carbon and iron, so which does not allow the these diamond-like coating to be formed on these HSS and the stainless steel kind of material. So you need to have some sort of surface modification to improve the adhesion between the coating and the this thing. Now we will take an example of, for example, a stamping tool. A stamping tool either you can have in your mechanical engineering or like a stamping tool which is used in the minting of the coins. So what you find is that they use some sort of steel, which is hardened steel, and then there are dies wherein you can print for example, if you want to print one rupee coin, so we can have the Ashoka emblem on one die and the denomination of one on other die. But you will find that if you go to a mint factory, they produce about 10 lakh coins in a day. So if you use this tool without any coating, we'll find that after some time, the impression of this Ashoka emblem as well as that of the denomination of the currency, that is say 1 rupee or 2 rupee, it gets diminished. So to improve the life of these tools, you find that you have to apply certain coatings. So that coating should be highly adherent and just one. The coating should be highly adherent, and then it should be very tough, and also it should have very high hardness also. So towards that, we are developing various nanocomposite Supertough coatings for particular applications. Herein, we are not bothered too much about the hardness. We need moderate hardness, which is about say 20 to 30 gigapascal, but the toughness is very high, which is about say 4 to 5 megapascal meter per hour. And then you find that in this, for example, if you take conventional ceramics, wherein you find the mechanical properties are very good, but then the fracture toughness is very, very poor. So if you apply some sort of an indentation, you'll find there will be a lot of cracks will be there. But in these kind of nanocomposites, you'll find that there are no cracks as a result of application of some sort of external force. So, so these are some of the typical. You can see that we have compared here some of the coatings, and you find that the performance of the coated tool improves by a factor of 50, which is very, very important. And you can see here a Mnemonic 75 a turbine hub, which has been machined by using these coated tools. The another aspect is the development of diamond-like carbon coatings. You know that in most of the aerospace sector nowadays, the carbon composites are being used because of the weight as well as because of the strength issues. But the machining of carbon composite is very, very difficult because of these composites. There will have fiber structure, so we need highly specialized coatings which have very high hardness, very low coefficient of friction. So towards that, we develop various diamond-like carbon coatings using various processes. And these are some of the tools. That is just to show you that what are our capabilities, like for various compressor blades, shank tool, drill bits, a tapping tool, inserts, a large number of gears. They can be coated by using these PVD processes. Again, we have done a lot of work for the India government mint. We can also develop these coatings for piston rings, wherein you need very high temperature of about 700 degrees Celsius because the conventional chrome plating it does not give you very high hardness. So the newest bike nowadays in the market, they are having piston rings which are coated with these PVD processes because of the two reasons. One is the hardness is very, very high. The second thing is that their stability is also very high, up to 700 and 800 degrees Celsius. As a result, you find that the operational temperature of your engine can be increased up to 800 degrees Celsius, and subsequently you find that your engine efficiency increases and the fuel consumption improves, and subsequently you find that the your pollution levels are decreased in the environment. So these are some of the applications of these kind of coatings. There's another applications which has been done for DRDO, wherein they wanted to use these coatings for the cryocooling applications for the night vision camera. So this coating technology has been given successfully to DRDO. This work we are doing for Titan Industries. You can just see that whatever the watch, wrist watches you are wearing, there will be some golden color coating. That golden color coating is nothing but titanium nitride coating. The titanium nitride, how it is formed? We take a titanium plate, and then nitrogen is allowed to flow in the vacuum chamber, and then this nitrogen reacts with titanium atoms. It forms the titanium nitride. It has a golden color. You can have any other kind of colors. For example, green color you can have black color. You can have you can have brown color. You can have golden color. Any kind of color, depending upon the. You can control the flow rate of the reactive gases. You can flow either nitrogen. You can flow methane. You can flow a combination of the nitride, nitrogen, and oxygen to achieve various kind of colors. So these are some of the. You can see that some of the. Of course, the photograph here is not good. You can see here more clearly. Everything is done in the lab. So in a very controlled way, you can achieve these kind of coatings. So just for the sake of the audience, this technology has been transferred to Titan, and the most important aspect here we have to see is that the corrosion is very, very important, because the human body, whenever this watch is in contact with the human body, there will be a lot of just 1 minute. So somebody is trying to. Okay, so what will happen is that a lot of because of the sweating, there will be a lot of salts will be there, and then they react with this material, and then you find that after some time a lot of corrosion materials will be there. So we want that corrosion to be inhibited. So we have developed highly specialized kind of coating, wherein not only the appearance but also the corrosion aspect as well as the wear aspect is taken care of during the deposition of these, during the development of these coatings. The other issue wherein these coatings can be used is in the turbine engines. For example, if you take a fighter aircraft, then you find that yesterday you might have heard in the newspaper that our Rafale is coming through the Middle East, and then it will be landing today. In the Middle East, there is a lot of dust is there, a lot of sand is there. So when the aircraft goes with very high velocity, then what will happen is that there is a lot of ingestion of sand into the compressor blade and the turbine blade. So what happens is that there will be the life of the blade gets damaged, or the blades get damaged, and then subsequently you'll find that you need to replace these blades frequently, which is a very Herculean task. You are aware the cost of these fighter aircraft is very, very expensive. For example, say 12,000 crores or that kind of, or 15,000 crores for one aircraft. So their maintenance also becomes very, very difficult. More so, the engine maintenance becomes very difficult. So if you want to avoid these kind of problems, or for example, when our LCA, light combat aircraft from Bangalore is going to somewhere in Ambala or in Rajasthan, you'll find that a lot of dust will be there, and that dust will be accumulated in the compressor blade, and because the speed of the compressor is very, very high, so there will be a lot of damage. So you want to prevent that damage, so we apply a large number of coatings. So there are a lot of solutions are there. So we have come up to a third generation coatings, wherein we apply either the nanocomposite coatings or nanolayer multilayer coatings on these kind of things. So this is a patented coating technology. It has been given to GTRE, our DRDO lab, wherein you find that in the next slide I show you that the the performance of this blade, which is shown over here on the right hand side, a typical turbine blade. You can see here the damaged portion of the turbine blade, which needs to be changed. And then this is a coated turbine blade over here. Then you find that on the left hand side, this one graph is there. The performance of the coating, you can find that the performance of these compressor blade improves by a factor of about 100 when you apply a very thin coating of say 5 to 10 micron of these kind of coatings. So it's a very kind of you can save money as well as time to run your aircraft. The other aspect of the coating which you use in the aerospace application is the solid lubricant. In the mechanical engineering, all of you use lubricants like some sort of grease, sometimes you use oil. These materials cannot be used for high temperature applications or for satellite applications. For example, you want to send a rocket from VSSC Trivandrum to in the space. So, and there are some bearings which are exposed to both the atmospheric conditions, such as in the VSSC Trivandrum, or in the space conditions, wherein the humidity is zero, but the temperatures are very, very low. So your conventional grease and all those things, that is not going to work. So what people are talking about is that they use for our routine engineering application, we use either graphite, like the solid lubricant. We also use, for example, molybdenum disulfide or tungsten disulfide. This diamond-like carbon coating or the graphite coating, it works only when there is some sort of humidity. So it will work only in the ambient conditions. It cannot work for the space conditions. If you take these solid lubricants, other solid lubricants such as molybdenum disulfide, then you'll find that they will not work in the under ambient conditions, but they will work only in the space applications. So now the problem is that, for example, in the next slide you will see this is a typical rocket which is being launched from ISRO. There are certain sort of bearings which are getting exposed to not only the atmospheric conditions but also the outer atmospheric condition, that is the space conditions. So for that we have designed and developed various nanostructured solid lubricant coatings, wherein these tungsten disulfide or molybdenum disulfide, which you call them as the chalcogenides, they are doped with some sort of metal. We can have like titanium, we can have copper, you can have chromium, or for a space application we can have gold also. So you find that if you do this kind of thing, there will be a little bit of trade-off in the mechanical properties and the topological properties. So that means to say that if I take tungsten disulfide, it's a mechanical properties are very, very poor, but its topological properties in terms of the friction coefficient is very, very low, that is 0.05 or 0.06. But when I dope these tungsten disulfide kind of material with some sort of metal, then I find that there is a trade-off between the mechanical properties and the topological properties. But nevertheless, we can achieve friction coefficient as low as about say 0.1 and hardness as high as about 10 gigapascal, which is very good enough for most of the applications. Next is that whether, for example, most of the turbines, if you see, I don't know whether you have seen any turbine, you'll find that in the turbine there are a lot of micro holes are there. Mostly these mechanical engineers, they can appreciate that the diameter of these holes will be say maybe 100 to 1000 micrometers. So the question arises how to do these kind of drilling in Nimonic and in Kunal, because most of these engine materials are of like Nimonic and Kunal. So conventionally people, they have been using like laser drilling, but the laser drilling that has a lot of disadvantages because you find that there's a lot of heat formation and there is a lot of material buildup, and then as a result of that you find that a lot of stresses will be generated in the turbine, which you cannot afford because the turbine has to run for 25 years, and if there is a small amount of stress is there, it will try to generate over the years, and then after some time it will fail. Which we don't want to do that. So what we have done is that we have used these micro drill bits and micro end mills with a diameter of say say 100 to 800 micrometer, and then we have done the coating on various hard coatings. Here you can see that this is what I was talking about. If you take these laser drill holes, so you'll find that the the hole quality is not very good. There's a material buildup is there, or you can use EDM. But EDM, the problem is that it's a very cost intensive and it's a very slow process. So what we have to do is that we have to apply these kind of coatings on these materials, these tools, and then we have investigated drilling of various, for example, aluminum alloys, titanium alloys, and stainless steel material, and then you find that the performance of the coated tool improves significantly as compared to that of the uncoated tools. So yeah, so now the other aspect is that whether you can have some sort of surface modification. Yes, the answer is yes. For example, on the right hand side, you can see a lot of stamping tools which are being used for like LNT Swiss gear. If you want to make that, so you need to have these kind of stamping tools, and then to improve the life of these tools, what we simply do is that you put these tools in a plasma consisting of hydrogen and nitrogen and argon, and then you find that this nitrogen and hydrogen diffuses into the your bulk of the material to a depth of about say 30 to 100 micron. And then because of the nitrogen diffusion, there is a lot of nitride formation, which improves the mechanical properties and then the corrosion properties. So it's a very cost-effective process compared to that of the PVD processes. So these are some of the components which have been machined in my lab. You can see the mnemonic, you can see some of the turbine hubs, you can see aluminum alloys, you can see carbon composites, you can see TI6L4B. There are a large number of materials which can be machined efficiently by using these coated tools with the performance improvement. And also the other problem in the conventional machining is that you find that the surface roughness is sometimes not very good if your tool is not very sharp. But all these problems are sorted out if you apply a very thin coating on these tools, and then if you do the machining. Now the question arises that how to upscale these things. So what we can do is that, because if you go to industry, for example, any of your, I don't know, nearest your industrial town, if you go there, you'll find that in one batch, they will do about say 10,000 tools they will coat at one time. And these are PVD processes. So what they do is that they have used vacuum chambers, and then they are pumped by using very high capacity vacuum pumps, and then the planetary motion is used to coat these materials. So we can have batch production, we can have inline production. For example, if you take one kind of a strip and you want to coat say 1,000 of meters continuously, so what you can do is that you can have the inline sputtering system. So you keep on feeding the strip of metal, and you keep on coating, and then after some time the coating comes out, the strip comes out with the coating. So there are large number of, depending on your applications, you can design your vacuum chamber, you can design your sputtering system or the PVD coating system. So this is the thermal barrier coating, which is another important aspect in the aerospace sector. It's a huge, about $40 to $50 billion industry worldwide, and
Sir, requesting, sir.
Sir, maybe we'll wait, sir. His signal might be lost.
Okay.
No problem. He may rejoin, sir.
Okay.
Madhivanan sir. Intimate பண்ணா better.
Yes ma'am, yes ma'am, please ma'am.
Intimate பண்ணா better இல்லையா சார்? சார் அங்க கிளாஸ் எடுத்துட்டு இருக்க போறாரு.
புரியல மேம், லிங்க் புரியல மேம்.
சார் அவங்க ரிலீவ் ஆனது அவங்களுக்கு தெரியுமோ தெரியாதோ கூகுள் மீட்.
அதான் இப்போ ஹெச்ஓடி சார் கால் பண்ணுவார் மேம்.
பேசுனாங்களா? ஓகே சார். அதான் ஃபோன் பண்ணேன்.
ஓகே. Dear participants, regretting for the interruption, there is a network problem. Meanwhile, I request a participant, if you are willing to disclose your feedback, please convey with us. Meanwhile, I request participants, please, if you are willing to share with your feedback, please unmute yourself and you can speak. Please wait for 2 more minutes. A resource person will join again. Dear participants, please wait. Our HOD has contacted. Yes, sir, please, sir. Sir, your mic is in mute, sir, please.
Okay, sir, where it lost? Can you just tell me that slide?
Yes, it is a deposition of PVD coatings. Yes, deposition of PVD coatings.
Yes, sir. Yes, sir.
One minute. Where I am?
Sir, we are not seeing your presentation, sir.
What is there now? It's not sharing?
Yes, sir. Yes, sir. It is not sharing. Sir.
Okay.
Yes, sir. Now it's okay.
Yes, sir. Now it is okay, sir. But
Not in full
you have
screen.
to close that next slide and no notes that portion, sir. Yes, sir. Yes, sir.
Okay, why did I lost?
Yes,
looking-
yes, sir.
This is
slide
okay?
we have, this slide we have you have explained, sir. Next one, sir.
This
This is
one?
also over. This is also over, sir. Next one, sir.
This one?
Yes, sir. Yes, sir.
Yeah.
Plasma
Here only.
nitrogen, yes, here only, sir. Here only, sir.
Here
Okay,
only,
so
sir.
you can call me. Now you can call me if any problem is there. Okay.
Sure, sure, sure.
My phone number is there, right?
Yes,
Hello?
sir. We are having phone number with our HOD, sir. Yes.
Yes, sir. Yes,
Yeah.
sir.
You can note down 9591.
Yes, sir. I have number. I have your number, sir.
Okay, so I will again. I'm sorry for that inconvenience. So what I was talking is that instead of these PVD coating, you can also do surface modification of your tools. For example, you use this M2 and M42, wherein you find a lot of cobalt and other kind of material is there. So if you want to improve the mechanical properties in a cost-effective way, what you do is that you keep that thing in a vacuum chamber, wherein you create a vacuum of -3 millibar, and then you allow some nitrogen and hydrogen gas to flow in. Then this nitrogen, and you create a plasma. Plasma, as I mentioned, that is nothing but the fourth state of matter, wherein you'll have these nitrogen ions and hydrogen ions will be there. So this nitrogen in the form of atoms, it will be diffused into your core of your material. For example, take mild steel or tool steel. So then you find that the composition of that diffusion layer changes, and it has properties different from that of the core material. We call it as a diffusion layer, which is about say 30 to 100 micron, depending upon the process parameters. And then you find that on the right hand side, I have shown you some of the tools which are plasma nitrated, and then you find that they can be used for many of the like blanking and other kind of applications. There's another way wherein you can use the PVD technology to improve mechanical properties. So here are some of the photographs. You can see that we have machined in my lab inconal, pneumonic, some sort of turbine, have aluminum alloys, carbon composites, Ti6L4. The large number of materials have been machined in the lab using these kind of coatings. And the most important aspect is that the life of the tool increases very, very high, but the quality of the hole becomes very, very good. The surface roughness of the drilled area becomes very, very smooth if you apply very small coating on these kind of materials or these kind of tools. So this is a typical kind of industrial systems wherein you find that about 10,000 of cutting tool inserts or the drill bits can be coated. So there are state-of-the-art facilities which can be used to develop these kind of new materials. Now these technologies are very common. If you come to any Bangalore, you'll find that in Kenya there are lots of these kind of systems wherein these PVD coatings can be coated for various applications. So this is another application of like coatings, the thermal barrier coating. You know that it's a very gas turbine engines are about $40 to $50 billion industry worldwide. Now, to improve the performance of any turbine, you find that you have to increase the operational temperature. So typically, you use about 1,200 degrees Celsius. But most of the materials, metallic materials, which are currently being used to design these turbines, they are not stable at temperatures beyond 1,200. So for typical gas turbine applications, the temperatures required are about, say, 1,400 to 2,000 degrees Celsius. So the question arises how to achieve those kind of temperatures. So the solution is the area of thermal barrier coatings, wherein they are stable up to, say, 2,200 to about 2,500 degrees Celsius. So you can increase the efficiency of your engine, and then it also reduces your pollutant gases such as carbon monoxide and NOx kind of gases, and it also decreases the fuel consumption. So there are a large number of ways. I'm not going to the detail how to do that one. The basic guiding principle is that we have to have a material wherein the thermal conductivity of the coating is very, very good. So is it okay? Am I audible?
Yes, sir. Yes, sir.
Okay. There's another applications that drag is a very serious issue in any of the aircraft. Supposing, for if you go to sometime in some sectors, you'll find there will be a lot of turbulence will be there whenever there's a bad weather is there. So that is nothing but the drag comes into the picture. So it disturbs the flow of laminar flow, we call it in the aerodynamics of the aircraft, and as a result of the control of the aircraft becomes very, very, very difficult. So the pilot has to kind of maneuver in such a way that he comes out of that particular thing. The other thing would be that in general, if you can reduce the drag of any aircraft even by 5 to 10%, then you can do a lot of saving of the fuel, and the efficiency is also increased. So here we have shown a typical example that you create some sort of plasma on the wings, and then you find that the drag improves or reduces by about, say, 10%, which is very, very significant. So yeah, here I was there when I left. So this is the another application of these coatings. Many times in the winter, this thing, if you go to Western countries, that whenever the aircraft is parked, you find that a lot of ice is deposited on the whole aircraft as well as on the windshield. So especially in the cold countries, this ice or snow can be a few inches to a few feet. So to remove that ice becomes very, very difficult. And for example, whenever you are driving a car and suddenly if the rain comes, you have to switch on your wipers. Now, hypothetically, if you think about that, if you have a coating which is water repellent and ice repellent, then all these kind of problems can be sorted out. So we work on a variety of coating technologies wherein we can develop this transparent, sprayable super hydrophobic coating and anti-icing coatings. So wherein all these problems can be avoided. Of course, there are a lot of challenges in terms of the stability of these coatings under extreme environment, and the skilling of these coating is also very, very challenging. So a lot of work is going all over the world to address this issue. So this is another, you can see that many times you are using these high-tech specs, spectacles. You find that like in the night that glaring should not be there, anti-reflection coating should be there, the transparency should be very, very good. And then the fogginess, whenever you exhale something, then the fogginess, nowadays especially whenever you are putting mask, so whenever you are exhaling and if the humidity is very high, then you find that your glasses, they become foggy. So if you can think about a coating which is scratch resistance, which is hydrophobic, which is anti-reflection coating, which is anti-glaring, that kind of coating. So these coatings are already there in the market. So so we have developed these transparent super hydrophobic coatings. So they can be used not only for the kind of application I spoke, but they can also be used for like a lot of other niche areas such as your photovoltaics and the night vision optics or your IR thermal imaging cameras. This is another applications. For example, if you sit in any fighter aircraft, there is a canopy is there. So the canopy, the problem is that in the fighter aircraft there will be radar will be there. So the radar signal should not come out of the canopy. Otherwise, the enemy radar will pick up the signal from our aircraft, and subsequently there is a threat to the aircraft. So what we have to do is that we need a coating or a very transparent coating, which is not only mechanically robust, but also it has the electromagnetic interference property. So whenever the radar of a particular frequency comes, it will get reflected from this particular coating, and then our aircraft will be safe. Will be safe. So for that, we develop a large number of coatings. For example, one is the transparent conducting oxide. That is one of the coatings. Nowadays, people are talking about silver nanowires or conducting polymers. The other thing is that the geostationary satellites, which are kept at a about say 400 to 500 distance from the surface. So there also the heat management becomes very, very difficult because whenever the satellite is near to the sun, then you find that it absorbs a lot of heat, solar radiation, and then subsequently it gets heated up. So which disturbs the electronic components which are kept inside the thing. And whenever the satellite is in the deep space, that means to say that it is not seeing the sun. Then you find that the temperature will be very, very low. So there is something known as a heat management system for these kind of satellite. So there also large number of coatings are required, wherein the solar transmittance has to be very, very high, and the IR emittance has to be very, very high, because whatever the solar radiation falls on this particular rocket or the satellite, then you'll find that it gets reflected back. And the most important thing is that the sheet resistance is also has to be in very, very low. Generally, the sheet resistance can be low only in the case of metal, but metal, they are opaque. They cannot allow the transmission of the radiation, solar radiation, which is required for your solar panels to generate the power for your satellite. So this is another applications wherein these kind of coatings can be used. These are all nano coatings. Am I audible, sir?
Yes, sir. Clear, sir. No problem, sir.
Okay. So this is another applications that we do some sort of coatings for some satellites, wherein is sensor of mercury cadmium telluride is kept at a temperature of about 105 Kelvin. Now, to achieve that temperature, either you have to do the cryo cooling, but cryo cooling becomes very, very expensive in terms of that the enemy in the satellite is the weight. We have to reduce the weight. So if you do all these cryo cooling, the weight of the satellite becomes very, very high. What we have done is that we have given a very highly reflective coatings, wherein whatever the solar radiation falls on the detector, before it falls on the detector, it gets reflected about 99%, and then subsequently you find that effectively only less than 1% of the solar radiation falls on this particular detector, and then you find that the temperature of the cooler remains around say 100 to 105 degree Kelvin. And please note it there, the roughness of this coating is about 2 nanometers, so it's highly reflecting. The specular reflectance is more than 99% for this kind of coating. So this I have already explained you that these ITO coatings, for example, indium tin oxide coatings, they are used in most of the flexible optical solar reflectors. They are used not only in the satellite industry, but they are also used in the your solar cell applications. We deposit these coatings by using sputtering of, say, if you take indium tin target and then you sputter this target in the presence of argon and oxygen. Just by controlling the process parameter, you can control the transmittance, you can control the conductivity, you can control the mechanical properties. So some of the optimization is done over here by controlling the various parameters. For example, the flow rate of oxygen, the flow rate of argon, and you can control the seat resistance as well as transmittance, which are two important properties of this material. So here again, you can control the sputtering power, the way the material is ejected out from the target material. So this is a typical thickness. You can see that we can develop these coatings wherein the thickness can vary from, say, a few tenths of nanometer to a few thousand of nanometer, and then subsequently on the right hand side you can see the cross sectional FESC images, wherein the thickness of this coating is about 1 micron, 1000 nanometer, and on the lower hand side you can see the thickness of this coating is about 200 nanometer. You can go down to even few nanometer also, and here is the typical surface toughness of these kind of coatings. So I'm not going into the details, just to show you that how important these coatings are there. They are all nano coatings for various applications. So this I'm going to skip. So now I will, So now I am going to come to this wavelength segregators. So this, most of my mechanical engineering students, they use it in most of the solar cell applications. You find that you use only the solar radiation. That means that visible radiation. So about, say, 400 nanometer to about 800 nanometer. Now, what happens to the other radiation? Because solar radiation starts from, say, 200 nanometer to 2005 nanometer. So especially the IR part of the solar radiation that generates the heat. So whenever the solar radiation falls on any solar cell, you find that in addition to absorbing the in the visible region, you find that the IR also gets absorbed, and then you find that after some time there will be a lot of heating will be there, and this heating is not good for the device because it reduces the performance of this thing. And another classical example you can see on the right hand side, this gentleman is seen over here. Mostly in the European countries, you'll find that, or the Western countries wherein the temperatures are very low, in their windows there will be a special kind of coating there, which allows the solar radiation to come in. But whatever the heat is there inside the room, it cannot go, it cannot escape. So those kind of coatings, you will find that it can be transparent coating, it can be photochromic coating. So that thermal management of your room or your house becomes very, very important. So there also you find that some sort of coatings are there. So now coming back to this solar cell. So if you can segregate this visible radiation as well as the infrared radiation, this visible radiation can be used as the solar cell, and this the infrared radiation, which is nothing but heat, it can be used either in the thermoelectric devices, or you can have a separate cooling mechanism so that the performance of your solar cell does not degrade. So this is the kind of another applications wherein you can use these kind of coatings. So this I am not going to the detail. This is a little bit of physics is there. So now coming to, for example, nowadays a lot of people are talking about filtrations and then nanofiltrations and then water purification. So there you need kind of membranes wherein the diameter of the pore size is few nanometers. So what we have done is that we take a simple, am I audible, sir?
Yes, sir. Yes, sir.
So we take a simple aluminum foil, which is about, say, 25 micron, and then we do some sort of chemical treatment, And because of this chemical treatment, I will show you in the next view graph. You can see the very fine holes of, say, maybe about, say, 50 to 100 nanometer, which is a very this thing. And then the membrane thickness can be varied from, say, few nanometer to few tens of micrometer. Few tens of micrometers, there is no problem in handling, but when the membrane thickness is very low, the handling becomes very difficult. But nevertheless, these membranes, their physical strength is very good, so they can be used as a freestanding membrane for various applications. For example, here you can just see that we use this membrane to develop various nanodots. You can, in the next slide, you will see that you can also develop the nano wires. The nanowire dots are basically used in your computer hard disk. Here, typically, I have shown samarium cobalt, which is a magnetic material, and is being used in the your hard disk. You can have gold nanodots, you can have cobalt nanodots, you can have any kind of material just by using these templates as a growth mechanism. So the other thing is that, for example, you want to nowadays. People are talking about detection of this COVID virus. Similarly, we have to detect various other kind of bacteria, such as E. coli or malaria-infected cells. So what people are doing is that they are trying to use both the combination of nanoparticles, metal nanoparticles, and the nanowires, silicon nanowires in this particular case, you can just see. And they use the principle of SERS, that is surface enhanced Raman spectroscopy, which is based upon the principle of the Raman spectroscopy or Raman effect. So we find that this technique can be used very high, with very high sensitivity. For example, even one molecule of this particular cell can be detected by using this particular sensor. So this work we have been doing in collaboration with our academic partner in JNCSR in Bangalore itself, and the sensor is ready for various applications. Now switching over to a little bit of other applications. So we, as I mentioned in the beginning of my presentation, we have competence to develop various nanopowders, and which are in their diameter is in the micron range or in the nanometer range. So we use combustion synthesis method, and then we can vary the size of these particles starting from few nanometer to few micrometer. And these powders can be subsequently used for various other applications. I'll just show one or two applications. For example, this here is the alumina substrate, which are used in substrate applications. Mainly for high power electronic, this thing, for example, aluminum nitride and YSZ tapes for SOFC applications. So these powders, they are formed in the form of slurry, and then the slurry is casted using a tape casting machine. So we can achieve a film of thickness about, say, a few hundred micron to, say, a few millimeter thickness. Then you can have these substrates, and on top of that, you can deposit these electronic devices, high performance electronic devices for high frequency applications as well as for high temperature applications. So this is another applications wherein we have developed this tape for VSSC program, and then one of the industry QME, that technology has been given for production. So now I'll just come to this last leg of my presentation, wherein we use CNTs and graphene for various applications. So graphene is nothing but a single sheet of carbon atoms. And if you fold it in 0 dimension, we have quantum dots. If you fold in 1 dimension, then we have carbon nanotubes. If you fold in the multilayer stack, then you find that there's a graphene. So in the CNT, we can have single wall CNT, we can have double wall CNT, we can have multi-wall CNTs. So these are very interesting material. They have very interesting properties, not only very high electrical conductivity, but also thermal stability, as well as um, um, the broadband absorption. So which I'll just try to cover over here. So this is a typical, if you see CNT, they'll be black. So that means to say that they are absorbing whatever is falling on them. But if you see CN graphene, it looks transparent. You cannot distinguish between the transparency sheet and the graphene. So here the transparency is very, very good. So if you can combine the properties of graphene and CNTs, then you find that you can improve the properties of a given aerospace material. Just to give an example, that if you allow, say, 5 to 10% of CNT as well as graphene in any composite material in the aerospace sector, then you'll find that the performance improves by a factor of, say, 2 to 3, so which is very, very large. So here in this case, we use a CVD process to develop these CNTs, and we can control their thicknesses, we can control their diameter, we can control their other properties just by controlling the process parameters. So this is a schematic wherein we have a substrate, then we have a adhesive layer, then we have an intermediate layer, then we have a diffusion barrier layer, and then just by controlling the process parameter, we can control the properties of the CNT in the form of coatings, not in the form of powder, but in the form of coating. So they have a lot of applications. Of course, this application here has been listed for photothermal conversion applications. That means to say that this material can absorb the solar radiation and that it will not re-emit the solar radiation when it gets heated up. We also work on graphene kind of coatings. These are again very interesting materials. They have very good, they can be used for various applications such as field effect transistors, transparent conducting electrodes, photo detectors, and then the invisibility cloak. We hear many times that there's a fabric wherein when you put on that fabric, you get invisible. So that kind of fabric is designed based upon these graphene kind of material. So we can have monolayer graphene, we can have bilayer graphene, you can have multilayer graphene. So depending upon the process conditions and depending upon your application, you can produce these kind of materials at your will. And then subsequently, you find that the other derivative of graphene is the reduced graphene oxide, which is more easy to prepare, and the graphene oxide, which is in the form of powder. This powder can be dispersed in a suitable medium, and you can find various applications. You can form various coatings out of these kind of materials. So this is what I wanted to share with you. So before I conclude, I'd like to thank the management, my various collaborators from India as well as from abroad, my students and colleagues and various funding agencies who have supported this research. If there are questions, I'll be very happy to take the questions.
Yes, sir. Thank you, sir. Shall we go for a question and answer session?
Yeah.
I request the participants, please unmute yourself and you can ask questions to our resource person, or you can type questions in the chat box. We will ask on behalf of you.
So shall I minimize that one where the chat box will come?
Yes, sir. Yes. No problem, sir. You can minimize and the chat box also will come. It's no problem.
Okay.
If any questions I found, I will ask you. Okay.
Yeah.
Once again, I request the participants, please unmute yourself and you can ask your queries directly to our resource person, or you can type the question in the chat box. Sir, it seems no questions, I think. Sir, please, one question, sir.
Please elaborate more about MOS.
Yes, sir, yes.
Can
Graphene
you,
in blue. Yes.
one question,
Please.
one question at a time. Can I get?
No problem, sir. I will read one by one, sir. First question, please elaborate about the MOS2 and graphene in lubricating area. This is the first question, sir.
What I was trying to tell you is that in most of your applications, we use graphite as the lubricant. It is because of the fact that it has a leafy material. That means the layered material. And if you see the lattice of graphite, you find that there are hexagonal structures. So there are different layers out there. So these layers are they have the property of low friction. Similarly, is the case with the MOS2 as well as the WS2. Now, the point what I was trying to make was that this graphite cannot be used for space applications because in the space there is no humidity. All these carbon-related materials like diamond or diamond-like carbon, they will work only when there is some sort of humidity. So to achieve that kind of performance, you can use these molybdenum disulfide or tungsten disulfide. Now the problem with these so-called dichalcozanide is that they work very well in the space environment, that means this inert environment, but they will not work when there is a moisture is there. So the solution, what we are proposing is that we can dope these tungsten disulfide or molybdenum disulfide to make them stable even in the moist environment. And but there will be a little bit of trade-off we'll have to do between the tropological properties and the mechanical properties. You find that just by doping say 5 to 10%, we can get the friction coefficient of about say 0.1 of the nanocomposite coating, and the hardness we can increase by a factor of about 10. So which is good enough for most of our space applications. So this is the answer of your question.
Thank you, sir. Sir, second question, sir. Sir, can we use molybdenum disulfide as TBC?
No, we cannot use it. It's a very unstable material. For TBC, the basic principle which I mentioned was that we are talking about a temperature which is about say 1200 to 2000 degrees Celsius. Unfortunately, this molybdenum disulfide is not even stable up to say 500 degrees Celsius. That cannot be used. You need mostly the oxides such as zirconium oxide or yttria stabilized zirconia or aluminum oxide, and some sort of doping of like rare earth material, which improves their mechanical their oxidation properties. But also one important thing is that you should, whenever you are talking about the thermal barrier coating, the thermal conductivity has to be as low as possible, because what will happen is that inside the turbine, if the temperature is say 1500 degrees Celsius, if the enclosure, even if it is stable and has a very high thermal conductivity, what will happen is that heat will get dissipated outside, so you will not be able to maintain that temperature. So the basic thumb rule is that the material should be thermally stable to a temperature to the tune of about say 1200 to 2000 degrees Celsius, and it should have low thermal conductivity. And also there are other properties, for example, hot corrosion properties, and all those issues are there. But definitely, in short, molybdenum disulfide cannot be used for that application.
Thank you, sir. Next question, sir. Salt gel method for prepare TBC is better than precipitating method?
Not really, because salt gel has a lot of limitation. As on today, they use mostly the thermal spray processes. That means to say that plasma spray processes or electron beam evaporation. If you go to DMRL, they will find that they use electron beam evaporation. But if you go to some industries, they use mostly either plasma spray, or they also use IOXY, SVOF, high velocity oxy fuel kind of processes. But definitely, sol gel process, it may give you some R&D data, but not for the kind of commercial applications.
Thank you, sir. Next question, sir. What kind of nano coatings are suitable for making good heat exchangers or radiators?
It's a very good question. You can have see the basic property which you have to look into is the emissivity should be very high. So most of these black materials, for example, this black coating, whatever you are doing by anodization, or like graphene kind of materials, or reduced graphene kind of oxide kind of materials, they will be very good for these kind of applications. If you see this, most of the radiator, either they will have white color or black color. That is because that the emissivity has to be in the controlled.
Thank you, sir. Next question, sir. Sir, can we use molybdenum disulfide as one of the components for thermal barrier coatings for gas turbine blades?
Sir, I think I have already responded to that question.
Yes, sir. Yes, sir. Yes, sir. It seems no question, sir. And all participants are telling that overwhelming thanks, sir. Thank you very much, sir.
Thank you very much.
Sir, requesting, sir, one more question, it seems.
Yeah.
Sir, please tell me the novel ceramic coating for TI6-AL4B by Magnetron sputtering technique to improve sliding wear resistance.
Well, I understood. You can do two kind of. You can do TI6-AL4B. You can directly do plasma nitriding. You will get all the properties: corrosion resistance, mechanical hardness improvement, and then the wear resistance you can increase. That is one way of doing that one. So directly you take a titanium TI6-AL4B plate and keep it in the plasma chamber, and then you'll find that after 2-3 hours after the diffusion layer is formed, you will find that all the properties mentioned, like corrosion resistance, the hardness, the wear resistance, will be always there in that kind of system. That is one way. The second way will be that you can apply some sort of coating. For example, you can have a titanium nitride coating if your temperature is not very high. So it depends upon what kind of applications you are looking for. If you have a particular application, I can recommend a specific coating.
Thank you, sir. Next question, sir. At elevated temperatures conditions, which one is more recommended, MOS2 or graphite coatings in aluminum basis matrix?
MOS2 is always preferable compared to that of the graphite.
The application is given for piston rings, sir.
Okay. In that case, MOS2 will not work. I'm sorry. Okay. So you have to use graphite only, because you need because in the piston you will have some sort of moisture will be there. So MOS2 it will form MOO3. This is not good for this thing. So for that you use graphite only, sir.
Okay, sir. Next question, sir. Pyroclare or AbO3, which material is good for PBC?
Nowadays they are talking about A2, B3O7, those kind of materials.
Sir, it seems in the chat box questions are over, sir. Sir, shall we wind up with vote of thanks, sir?
Sure.
Yes, thank you, sir. Thank you very much, sir. Your presentation added more value for this STTP program. Really, it is excellent presentation, sir. We have gained more knowledge about nano coatings on surface from your presentation, sir. We have started with physical vapor deposition, reactive Magnetron sputtering, and Superhard Nanocomposite coatings, and titanium nickel coatings, development of transparent hard coatings, the deposition of PVD coatings, plasma nitriding of engineering components, high temperature coatings, and ended with the wavelength segregator on solar cell, and it goes with the carbon nanotube, high temperature solar selective coatings. Sir, really we felt we have taken real virtual technical visit to National Aerospace laboratories Thank you very much, sir. Thank you. Thanks a lot, sir. Thank you, sir.
Thank you very much. I'm sorry there were some technical glitches were there, I think. But generally, I enjoy one-to-one interaction, but that is not possible right now.
Thank you, sir. Thank you very much.
Thank you. Bye.
I request participants, please join. Our today's session is over. I request participants, please join tomorrow 9:45 a.m. as usual, fourth day, first session. Rajesh sir, can you present tomorrow schedule, sir?
Sir, can you see my slide, sir?
Yes, sir. Yes, sir. Slightly zoom out, sir, please.
Okay, sir.
It is not visible. Yes, sir. Yes, sir. So the topic is functional nanomaterials for energy and environmental applications. Our resource person is Dr. Kamalakannan Kailasam and afternoon resource person Dr. P.S. Samuel. So I request all the participants to join with us tomorrow 9:45 a.m. as usual. Thank you for joining with us. I thank all the participants for joining. Thank you all.